Yes, very excited to present what we've been working on. Um, Thank you, Alec and Chaz, for allowing me to be a part of your research group. Thank you, Wanda, too, for being my academic advisor for the past 5 years. Um, and thank you, everybody who showed up, those in person and those on Zoom. So without further ado, let's get into this what we've been working on. Which is the winter foot traffic effect on annual bluegrass or Poa annual L putting greens in the Pacific Northwest. So these are some. I would like to acknowledge all of who worked on the study: Brian McDonald, Robert Starschvig, Chad Schmidt, and Sadie Duffy. I would also like to acknowledge the Bioresource Research Program that I am a part of, College of Agricultural Science, Department of Horticulture, and as well as the Turfgrass Disease Diagnostic Lab. Here in the bottom right, or we have a picture of Lewis Brown Farm, and then in that red rectangle is our study site. Um, so in this study, we would like to understand the turfgrass responses to repeated foot traffic during cold conditions. This would help improve management practices and also reduce long-term damage of turfgrass putting greens. And so in the Pacific Northwest, we allow, or they allow for, climates allow for year-round golf. So specifically during the winter and cold seasons. So there's a lot of public golf courses that actually rely on revenue and income during the cold climates. However, this is like a double-edged sword because from a management standpoint, you want as many people to play and but however, with lots of people, lots of foot traffic, that also correlates to more injury as well as an increased recovery time. So this is what we would like to what we're looking at in this study. And also, I also would like to mention that in the Pacific Northwest, several public golf courses have implemented a or reduced frost delays. So this means, in the cold seasons, there's frost in that turf grass. So um, because of this, a lot of people don't wait for that frost to go away. So frost can increase the susceptibility of injury of turf grass. So this is a concern for many superintendents um, regarding putting green quality. Um, so our study is looking specifically at annual bluegrass, um, which is commonly classified as a weed throughout the United States or throughout golf systems. However, superintendents in the Pacific Northwest have adapted annual bluegrass in their putting greens um, because of its uh, strong adaptation to regional environmental climates. So annual bluegrass is uh, adapted to the cool, wet climates that we have here in the Pacific Northwest, and it naturally persists in putting greens. Um, Fun fact, there's actually 500 known species of POA, and 60 of those species are actually native to um, North America. And here on the left is just a map of the US and like where cool season grasses usually grow, and then the transition zone, and then lower US is warmer um, species are adapted to warmer climates. So in our study site, we used a sand-based root zone design, which is typical for standardized golf course putting greens. So this design is specifically to limit soil compaction, as well as increase water infiltration rates. So we have the putting greens up top on the surface, and then below that is around 12 inches of sand layer of 12 inches, and then below the layer of sand, we have a layer of gravel about 4 inches of depth, and then below that is a drainage system just to um, increase for water infiltration rates. Um, So for this study, we're looking specifically at human foot traffic during cold conditions or under frost conditions. However, little information is limited. Or so, um, however, there has been lots of mechanical disturbances used to simulate foot traffic, but not for putting greens, but specifically for um, like soccer fields and football fields where the height of the grasses tends to be a little higher. But again, more research for foot traffic under frost conditions is needed for better recommendations for golf course managers. So again, traffic simulators. So here are a couple pictures of traffic simulators used for football fields and soccer fields, again, on higher um, more lengthy turf. And then here is a picture of a Caddy traffic simulator and then a Rutgers traffic simulator. And then we also have a photo of a Brinkman. So this actually simulates, like when you walk, it simulates or tries to replicate um, that little, like when you kick your foot out when you're walking. So that's what the last roller is there for. And then we also have a Baldry that right here you can see there's like little spikes that what we call a foot. So there's 4 feet on the machine, which hits the ground and simulates lots of foot traffic. And similarly with the caddy, and then the Rutgers has feet as well that simulates uh, foot traffic. However, there is not really a mechanical foot traffic simulator that can be used specifically for turf grass putting greens, which is why we are looking at foot traffic. Um, so our foot traffic pattern, we tried to simulate, or we simulated 0 foot traffic, so 0 rounds of golf per day, 50 rounds of golf per day, and as well as 100 rounds of golf per day. So we had, this is like our foot traffic pattern. We can see that there is numbers that indicate, how many passes. So we go up 1, 2, 3, 4, and then we did that again. So 2 of these, so 8 passes, um, simulates 50 rounds of foot traffic. So we did this at 8 in the morning and then again at 1 p.m. So this would be the 50 rounds of golf. And then we did it 2 more times to simulate 100 rounds of golf. And then here is a picture of our study site at Lewis Brown Farm. So this has been used it's been used or under USGA, so United States Golf Ball Association specifics sand greens. So as I mentioned before, the sand-based root zone. So this has been up to date with the USGA for 7 years. We mowed at a height of 0.14 inches, which is standard height throughout general golf courses. And then we had each plot was 4 feet by 20 feet. And fungicides were also used to control diseases, so such as microdochium and yellow patches, which are common diseases for during winter. And we also used a true turf greens roller every 2 to 3 times per week in order to smooth out surfaces and to simulate standardized golf course management, traffic, and playing conditions. So this is what it looked like. Yeah. Um, moving on, as I mentioned, each plot is 4 by 20 feet. We had a total of 12 plots. We did 3 plots per rep and 4 lanes. Uh, so here is our 3 plots. Photos were taken on January 8th. So our study started on January 6th. So 2 days after our initial start date. And then we can see that here you have 8, so representing 50 rounds of golf per day, and then 0, no traffic, and then 16, the amounts of traffic. So right now we see that, you know, visually they all look relatively the same. Um, and then, as I mentioned before, 12 total paths or plots. We had 6 disturbed paths and 3 controlled paths. So 6 being 50 rounds and 100 rounds, and then the controlled paths were no traffic, so 0 rounds. Here is a picture of our plots. So here we have 4 rows, um, which we walked up and down, and then again up and down 4 times, just to make sure that we have even distribution of foot traffic. And then the photo on the right is Brian and Sadie, who um, have been doing most of the foot traffic trial. So at 8 in the morning, and then again at 1 p.m. And then you can see right here that there's lots of indentations, so lots of uh, foot traffic. And then we used standardized soft spike golf shoes, which are different from regular cleats like soccer cleats or football cleats. So at the bottom, there's actually, you can see here, soft spikes. So it's like a little circle with like teeth at the bottom. Um, yeah. We also collected data from weather stations. Right here on the right is the Atmos 41 all-in-one weather station, which collected wind speed, direction, air temperature, relative humidity, as well as atmospheric pressure. We also used Teros 11 to measure soil temperature at a depth of 2 inches and soil moisture. And this isn't pictured here, but it is actually below the weather station. We also used the Gentra ZL6 data logger, which is this right here. And they recorded the atmospheric and soil data every 10 minutes, every day. And then we also used a simple infrared thermometer to read soil or to read surface temperature at 8 in the morning, Monday through Friday. So visual data was collected. So we looked at quality and injury. So visual data is a common practice to assess turf grass quality and injury among the turf grass research as well as the turf grass community. So the visual data is rated on a scale of 1 to 9, with 1 representing dead or dormant grass, while a rating of 5, or while a rating of 9 is represents really good, best possible greens grass, and a rating of 5 is generally used as or generally considered as minimum acceptable playing quality. And so turf quality was assessed based on turf grass color, its density, uniformity, and overall visual appeal. And we also looked at injury. So that was also measured visually, as well on a scale of 1 to 9, with 1 signifying no injury and then 9 being um, completely dead. So for injury, we were looking more at the discoloration, the thinning, or just any dead grass in general, with any level of damage being unacceptable to golfers. We also used the NDVI meter. NDVI stands for Normalized Difference Vegetation Index. So this uses infrared light to measure how much chlorophyll is being reflected or absorbed by the plants, or in this case, turf grass. And this rating is measured on a scale from 1 to 0, with 1 being best optimal conditions, really green, and then 0 being, completely dead. So a higher number indicates more chlorophyll. So we use the NDVI meter to estimate plant health before visual symptoms or visual injury, um, before we could see visual injury. And so the NDVI, how it's measured, so it uses this equation, which is NIR stands for near infrared minus the red wavelength divided by the near infrared plus the red wavelength. So data, as I said before, was collected using the Centra Z06 and then analyzed in R using the LME4 package to perform repeated measurements uh, of ANOVA using linear mixed effects models. And so when significant effects or interactions were detected, 2 key correlation post hoc comparisons were performed to compare turf grass response among all treatments and across environmental conditions. Um, just to determine if there are any significant interactions between the rating dates as well as the treatments. Moving on, air temperature. So this is a figure of minimum and maximum air temperature in degrees Fahrenheit over time. So the y-axis is air temperature in degrees Fahrenheit, while the x-axis is just the dates. The blue line represents the minimum air temperature, and the orange line represents the maximum air temperature, with the dash representing the freezing point at 32 degrees Celsius. And then where the dash ends, that's our like the end of our trial period. So as we can see, during the month of January, we see about 2 weeks of days that were below freezing temperatures, which I don't know if you guys can remember, and during January, really cold. Um, then we also, following in the month of February, we also see a couple days that were below freezing temperatures. And then we also see another point in March, like end of March, another day of temperatures below freezing. Now moving on to soil temperature, the y-axis represents soil temperature at a depth of 2 inches, and then again the x-axis is the date. The baby blue line represents the soil temperature at 8 in the morning. So we see that um, looking at the minimum soil temperature in blue and the maximum soil temperature in orange, we see that throughout the whole study, it remained above a freezing point level, which is kind of makes sense because it is at a depth of 2 inches, so there's like a insulation happening, uh, meaning it's not really affected or not affected too much by the air temperatures. So, which is why we prioritize looking at the surface temperature at 8 in the morning, uh, because that is the same time as when we conducted foot traffic. So we also see that during from January all the way through um, late February, there's a huge period of surface temperature being below freezing point, and then after beginning of March until the end of the study, that's when we see that warmer temperatures, coming back up. But in the future, we would like to put um, the probe either at a depth of zero point 0.5 inches or 1 inch, just to more accurately assess soil temperature levels and what is happening below the surface. Um, Now, looking at rainfall over the entire study. So y-axis is the rainfall in total inches, while the x-axis again is the dates. We see that for from January all the way through early April, that it was pretty dry with actually a total of 10.9 inches of rain throughout the whole study. So, but we also see like relatively high amounts of rainfall on February 12th, again, February 26th, and then a lot on March 12th, and then again, March 26th. So, and I'll be talking a little bit more on that and relating that to injury in the following slides. So visually, at the beginning of the trial, this is what frost conditions look like. So this is January 13th, so a week after the initial trial period, and then January 22nd, we see light frost conditions compared to heavy frost conditions. So with light frost conditions, that's just the surface level. So when you're walking and doing foot traffic, you get like patches of turf grass that aren't frozen or don't have frost. And then compared to the heavy frost on the right, even with foot traffic, you don't see that frost goes away. You actually see a little bit more compaction, which uh, we can see that during the heavy foot traffic, there's a lot of indentation. And then next to that is actually the no foot traffic, so you can see that difference. And then the moderate foot traffic. And then here, just representing or going back to uh, the minimum air temperatures. So January 22nd was actually the second coldest day during the entire trial. So which is why we see heavy frosts. So here is a table of we did an analysis variance, which showed the interaction between treatments and the dates. So we used two key tests to separate traffic treatments on each date. So this table provides a summary of all ratings. So we have 31 dates, and we see that what we want to, the most important thing about this table is that for all treatments, that there were 0 out of 31 points. So there was in no point where all treatments were the same. Uh, and there was more than 50%, so 18 out of 31 points, in where all treatments were statistically different. And right here, it's just comparing the heavy foot traffic with moderate foot traffic, and then moderate foot traffic with no foot traffic, and then again, heavy foot traffic with no foot traffic. And then we also see that also at no point in the study, we saw that treatments with 100 rounds of golf and no foot traffic were statistically similar. Moving on to mean injury over time. So this is the graph of mean injury. So visualizing um, the last slide, we see that there is a increase in injury during the 100 rounds per day, specifically during the month of January, so the coldest month. And then we see a decline in injury for both 100 rounds and 50 rounds. Up until February 16th, we see a increase or spike in injury, and then it goes back down the following day, and then it kind of plateaus, stays the same, and then injury goes down again, so signifying recovery during early May, and then again it goes up gradually, but then ultimately at the end of the study, the injury goes down, and if we look at the 50 rounds per day, it actually recovers to a degree similar to the no traffic, whereas the 100 rounds of traffic doesn't quite get to that uh, degree of recovery. And here is a picture of, 3 weeks into the study. So here we can see the effects. So looking at injury, we're looking at the discoloration and patches, and we can see that in the heavy foot traffic, so 100 rounds, we see the most amount of injury with lots of dead patches, not visually appealing compared to the no traffic, where it's much more clean, and then 50 rounds of traffic where it's in between um, the 100 rounds and no traffic. But if we look at that section right there, we see there's a huge, lots of discoloration. And actually that is where when we foot traffic, we were walking and then turned around, pivoted, and then started walking the other way. So with the spikes, as if you guys can remember, the spikes they're like teeth, circle teeth. So as you pivot, you tend to rip up the grass in the crowns, uh, causing more injury. So if we look at this closer, so it's a picture of the same plot, same day, but just earlier, 8 in the morning, around 8 in the morning. So we see, bits of frost, but here we can see lots of discoloration, which is what we would expect with heavy rounds of foot traffic. Here are a couple more pictures, both a month apart. So February 3rd and March 3rd. Here we kind of see, if we compare both of the pictures, I think we see that February has more damage compared to March. So significant. So this is kind of like when we're getting into the warmer climates, we see a little bit more recovery. However, not to an extent or not to the level of no traffic. And and then looking back at injury over time during the month of January, why do we see a spike in injury? Well, if we look at the minimum air temperature, whether what happened during that period, we see again a period of about 2 weeks of air temperature being below freezing. We also see that the surface temperature at 8 in the morning is well below freezing as well. And looking at the total rainfall in inches, we see that there is not too much rainfall, but we do see, using January 22nd as a reference point, so the highest amount of injury. Before that, we have accumulation of rainfall, and then after January 2nd, there's no rainfall, so that could be an indicator of injury along with surface temperature and minimum air temperature. So here we also have another analysis of variance using Tukey, but this time for looking specifically at quality. And again, there was only 1 point out of the 31 points that showed no statistically difference between all three treatments. So all three treatments were statistically the same. However, we want to focus on 17 out of 31, which is more than half, that all treatments were statistically different. And then this is putting that more into perspective. So quality over time, again, as I mentioned before, quality was visually rated on a scale of 1 to 9, with 9 being best quality, 0 or 1 being worst quality, dead. And then we also see a similar correlation between quality and injury, where the highest amount of injury happened during January, and the lowest amount of quality also happened during January, and that extended to early February. But I also mentioned before that a quality of 5 is the um, minimum acceptance playing level for general golf courses, and we can see that throughout half the study period, on the 100 rounds per day, that that level of quality isn't acceptable. So, however, compared to the 50 rounds per day, that it stayed at a quality rating above that acceptance. And then we see, a gradual increase where all of them kind of come together, so they all have similar qualities. But that's to the end of the study signifying recovery. And then another analysis of variance, this time looking at NDVI response. Again, this time there's only 3 points in which all treatments showed no difference, so they were statistically the same. And again, more than 50, so 16, more than 50%, so 16 out of 31 points in which all treatments were statistically different. And here we have the 3 points at the beginning of the trial, which, which correlates to like them being all treatments being the same, but this is at the beginning of the trial. So where again, NDVI is a measurement of chlorophyll absorption and reflection, indicating higher NDVI, indicating green grass, great, and then lower NDVI score, meaning dead. So the y-axis is the NDVI rating, and then the x-axis is the date. And then we also see a similar correlation of quality and NDVI. So when quality goes down, that's when NDVI ratings also go down, which gives us, we do this cross comparison because we're doing visual data, and then we're also backing that up with our concrete measurements. But we also see lots of or a decrease in NDVI rating specifically for the 100 rounds through January, and then that goes along until early February, and then we see a gradual increase and then a spike in NDVI quality for all treatments around the 20th and the 24th of February. And you see that it kind of, during the warmer months, that's when quality begins to, or NDVI ratings begin to kind of steady out. And then at the end of the trial, so then all of them come to similar level of NDVI rating, but with the 50 rounds coming closer to that level of no foot traffic compared to the 100 rounds. And so, conclusion, almost there, you know. Well, so these pictures were taken on April 2nd. So our study period ended on the 8th of April, so a couple days. And here we see the the amount of recovery across all treatments. I think it's a little hard to see because of the, suddenly it got super bright all of a sudden. But if you guys squint your eyes, look closer, we see that during the heavy foot traffic treatment, that there is still little amounts of yellow patches, so signifying injury, and compared to the no foot traffic, and then the moderate foot traffic, so 50 rounds comes to a level of um, recovery closer to the no foot traffic compared to the heavy. So again, restating our conclusions, high traffic caused the most severe frost damage at 100 rounds compared to the moderate foot traffic and no foot traffic. We also saw that surface temperature at 8 in the morning, along with minimum air temperatures and total rainfall, were the best predictors of turf grass damage, of when turf grass damage would occur. And then it's also, I think you guys can see it better now. So, this is like the heavy foot traffic. You can see like a couple um, injuries, and then gradually gets better. But again, injury to turf grass took more than 3 months to fully recover due to suboptimal growing conditions. And most importantly, that turf grass managers should not expect turf grass to recover until environmental temperatures begin to increase. Some limitations of this study was that since this was looking at foot traffic under frost conditions, we didn't investigate the impacts of frost delays, which is a common practice in golf courses. So that is what we would like to implement during the following year, is just to compare um, the impact of frost delays and comparing that with the no frost delays. We also tried to implement the USGA, so United States Golf Ball Association, GS3 golf ball, which measures the trueness, the greenness, and the firmness of the putting greens, as well as um, firmness, greenness, smoothness of the turf greens. Um, and we tried to implement that this year, but due to technical difficulties, it wasn't possible. So next year we will definitely be implementing that. We also specifically use soft spikes. So there's other forms of footwear, golf footwear that a lot of people use, but in this specific study, we only use soft spikes. So it is unclear if whether or not other footwear would cause more impact or less, more injury or less injury during frost traffic conditions. In summary, no foot traffic is unrealistic in the Pacific Northwest because we do allow for year-round play. However, annual bluegrass putting greens may tolerate a more moderate level of traffic compared to high traffic under sand-based conditions. Our preliminary data suggests that air, turf grass surface temperature, and rainfall does correlate with injury, and we'd like to see what amounts of rainfall following the temperatures and how that would cause the most amount of damage. And ultimately, this would be So having more foot traffic in golf courses would ultimately be a facility level decision that needs to be made depending on budget constraints as well as golfer expectations. So comparing public golf courses and private golf courses. So public golf courses tr rely on just how many people get in their golf courses, how many people, that's their revenue compared to um, public or private golf courses where, their budget is much less constrained and have more resources. So that also puts a lot of pressure on public golf courses to allow more people or less people, uh, depending on uh, weather conditions. So thank you guys for listening. I would also like to thank our sponsors that supported our research. So the Oregon Turfgrass Foundation, as well as the Northwest Turfgrass Association, USGA Davis, and the Oregon chapter of GCSAA. Thank you, everyone. I think we have time for questions if anybody would like to ask some questions.